In this first example we encounter, we're randomly selecting 16 coffee shops. So the minute we read that, we know that we're importing some amount of information. That right there is N. And apparently we're going to measure the temperature of the coffee that's being sold. The sample mean of the temperatures is 162 degrees Fahrenheit. So immediately that information is going to be X bar. The sample standard deviation is 10. So the minute we read that, we know that's going to be little s. We want a 95% confidence interval. Boom, immediately we know that that's going to be C is equal to 0.95. And we want to construct a confidence interval for the population mean temperature of the coffee sold, where we have this final assumption that the temperatures in question are approximately, so there should be a word in here, normally distributed. Very important that we actually have that word, so an egregious typo. So what do we want to write, and what do we want to start by observing? Well, the step-by-step process we had on the previous page begins with us verifying some hypotheses. So let's do that first. The hypotheses we're going to verify are the following. We're going to write that since sigma, notice that nowhere in this problem did they mention what the population standard deviation was. So as it stands, sigma is unknown, which means we're in the context of section 6.2. We also know that we started off by indicating the word random. So we know that the sample that we're choosing is random. And we need either the temperatures to be normally distributed or we need the sample size to be larger than 30. We already know the sample size is not larger than 30, so we have to hope for the other assumption, and indeed, at the very end, we have exactly that. So, since sigma is unknown, the sample is random, and the temperatures are approximately normally distributed. The conclusion we can make here is we use the t distribution. Well, to proceed with the t distribution, the next step requires us to collect some data with an eventual intent on finding the critical value t sub c. So the way I'll organize my information here is I'll write the following. Since n is equal to 16, what that means is that our degrees of freedom is equal to 15. And therefore, with c equal to 0.95, we find that our critical value t sub c is, well, what is it? That's a good question. We're going to have to import this information, degree of freedom 15, with a confidence level of 0.95. We're going to, again, have to go all the way to that chart at the end of the page, at the end of the handout, and we're going to have to find that info. Fortunately, we don't have to go far, because the highlighted column was already 0.95, and the degree of freedom in question now is 15. So the corresponding critical value is actually just going to be one spot lower, 2.131. So let's import that information back into our problem. The critical value is 2.131. Thus, the margin of error, E, is by the definition of the formula, t sub c, the critical value, times little s over the square root of the sample size. But now that we have all the data, t sub c is 2.131. Little s, remember, was 10. We recorded that while we were reading the problem. And the sample size was 16, so we have square root of 16. And if you plug this into a calculator, you'll get that this is approximately equal to 5.3. So the margin of error for our confidence interval is going to be 5.3 degrees Fahrenheit. Therefore, if we add and subtract this margin of error to the sample mean x bar, we're going to get ourselves the endpoints of our confidence interval. So for starters, we compute x bar plus, we'll do minus first, x bar minus e, so that's going to be 162.0 minus 5.3. That'll yield 156.7. And if we do similarly x bar plus e, in this case, we're going to end up getting 167.3. So what that implies is that the confidence interval for the population mean, which remember is mu, is that mu is going to live somewhere between either 156.7 degrees Fahrenheit or 167 degrees Fahrenheit. Those are the endpoints of our confidence interval. Now, it is going to be important after we do all this math that we apply the appropriate interpretation of what this confidence interval means. And just as we noted in section 6.1, it is important that you use the right vocabulary when you write out your interpretation. The appropriate interpretation for this type of conclusion is the following. All this math means at the end of the day that with 95% confidence, the population mean we might ask ourselves, what does this mean computing? This is the population mean temperatures, or we should say temperature coffee being sold is lying somewhere between 156.7 degrees Fahrenheit and 167 degrees Fahrenheit. So this is going to be the appropriate conclusion for what we're doing. Now, let's take a look at another example where we're going to have to do a lot of similar moves, but there's going to be one subtle difference. Here, we're randomly selecting 36 cars of the exact same model that are being sold at a car dealership. And our question is, we want to know the number of days that each car sat on the dealership's lot before it was sold. Again, we're given some pieces of information right off the bat. 36 cars, that's our sample size. We might note right off the bat that indeed the selection is random. We've already been told that the sample mean is 975 days, so we know that that's going to be x bar. The sample standard deviation is 2.39 days, that's little s. We want to construct a 99% confidence interval, bam. We know that C here is 0.99. And we want to construct this 99% confidence interval for the population mean number of days the car model is sitting on the dealership's lot. As we proceed, we're going to have to determine what tool set we want to adopt. This goes back to question number 1 in our construct a confidence interval list, which is verify that all of the hypotheses are satisfied. If you think that this is sort of a boring step, that's fine. It is somewhat boring, but it is absolutely imperative. In this instance, what we might notice right off the bat is, again, the population standard deviation, sigma, is never told to us in any way. So we're going to start by writing that since sigma is unknown, meaning, of course, we're again in the context of section 6.2, the sample is random. That's what we highlighted when we read the problem. And unlike the previous problem, where we noted that the data points were approximately normally distributed, that was not assumed here. There's no assumption on the sort of normal distribution of the data points. However, we're fortunate that that's not the only requirement. Remember that your population can either be normally distributed or your sample size can be large enough, greater than or equal to 30, such that the central limit theorem tells you that it's going to be approximately normally distributed. And in this case, what we're going to recognize is that n, which is 36, is of course greater than or equal to 30. So what that means is we are in the appropriate context to use the t-distribution. Now we can start writing down our information, finding our critical values, finding the margin of error E, and then finding a confidence interval. Now, we'll do it exactly the same way we did the previous problem. If n is 36, so we'll say if n is equal to 36, then our degrees of freedom is equal to 35. So, with C being equal to 0.99, our critical value T sub C is going to be equal to something else. Again, we have to reference our table. So we have degree of freedom 35. Our confidence interval is 0.99. Let's jump down to the table and see what we get. So in this instance, we'll highlight in orange, we're going in 0.99, so that's going to be this column. And we want to go all the way down to a degree of freedom of 35. So that's going to be down here. So the row that we're going to be looking at is right there, which means that the point of intersection is 2.724. We're going to take that critical value, T sub C, import that back into our problem. T sub C is apparently now 2.724. Therefore, we now have enough information to compute the margin of error E. Therefore, E, remember the formula is the critical value TC times the quotient S over the square root of the sample size n. And in this case, it's going to be 2.724 times the little s value, which when we read the problem, we interpreted as 2.39. And we divide that by the square root of the sample size, which is 36. And if you compute this on a calculator, you'll get approximately 1.09. What this implies, of course, is that if we compute x bar minus E, x bar was 9.75. That was inferred based on the problem. We're going to do that minus 1.09, which is going to give us 8.66. And of course, if we compute x bar plus E, that gives us our right endpoint of 10.84. So the confidence interval that we've built will have the population mean somewhere in between, and on the left it'll have to be bigger than 8.66. On the right it'll have to be less than 10.84. And this will generate our confidence interval with a confidence of 99%. Of course, we want to interpret this properly for the non-math observer. So we write that, meaning that using the correct verbiage, we write that with 99% confidence, the population mean, what does the population mean? Well, what we're concluding something about is the population mean number of days the car, we'll say the car model, because we focused on one single car model. The car model sits on the lot before being sold is between 8.66 days and 10.84 days. That's the conclusion. Where again, we're being very careful about using verbiage like with 99% confidence. As we saw in last lesson, we want to be careful and wary whenever we use the word, say, with a probability of 99% or something like that, because it's very easy to state incorrect conclusions. Now, we've learned all this content in 6.2, and the content in 6.2, as I keep referencing, assumes that sigma, the population standard deviation, is unknown. It's important when you encounter sort of real-world problems that you recognize that you have to do two different procedures depending on whether that sigma is known or unknown. And so we need to have it organized in our brain exactly how to proceed given a particular situation. As a result, there is an important note to make. And I made this earlier in this handout, but we'll make it again. We'll note here that in both situations, whether sigma was known or unknown, either way, you still need the population to be normally distributed or your sample size needs to be sufficiently large. If either one of these, if both of these fail, then everything here falls apart, regardless of whether you know your standard deviation or not. So what I would recommend is when you tackle a random problem where you don't really know how to proceed, it all comes down to verifying the hypotheses, and that should point you in the right direction. So this example would be representative of how we should start our train of thought. So we start by reading this and we read, okay, we randomly select 25 newly constructed houses. So right off the bat, we know n is equal to 25. Note that that is less than 30, so we have to hope somewhere that something about these houses is normally distributed. Says that the sample means of the construction cost, boom, we magically know that X bar is equal to 181,000. And it says that the population standard deviation, that's important, the population standard deviation is 28,000. This is, of course, in stark contrast with any of these previous problems where the deviation we were looking at was sample standard deviation. Up here, we had sample standard deviation. So as soon as you read population standard deviation, that is telling you that, no, this isn't little s, this is actually sigma. Sigma is 28,000. So what that means is that we're not in the context of section 6.2, we're in the context of section 6.1. So the game is a little bit different. Now it goes on to say that assuming the construction costs are normally distributed, good, considering the population size was not greater than 30, we needed that statement somewhere. The question here is, should you use the standard normal distribution, the t-distribution, or neither? To construct a 95% confidence interval for the population mean construction cost. So we've already kind of reasoned so far in our head, but if we had to write something down, I might write down the following sort of bullets that we just thought of. The first question we have to ask is sigma known? That means, are we in section 6.1 or are we in section 6.2? In this case, the answer is yes. So that means we are in the context of section 6.2. The next question that you might want to ask is either we need one of the following two things to be true. Either the population is normally distributed. That's one option. Or you need your sample size to be greater than or equal to 30. is do one of these things occur? The answer is yes. The population is normally distributed. We had that assumption right here. It is also important that we note that the selection process of the sample was random, and therefore at the end of the day, to answer the question of what distribution we use, if any, we find that we are going to use the standard normal distribution. Oh no, that means I made a mistake here. When I wrote that the sigma is known, the answer was yes. That shouldn't be the context of 6.2. That should be the context of 6.1. And that's why we're going to use the standard normal distribution to solve this problem. And then, of course, we'd refer back to the content that we learned in section 6.1 and the procedures that we learned there, and that'll help us learn how to answer and continue reasoning out this question to construct this confidence interval. This is going to bring a close to section 6.2. 6.2 is eerily similar to section 6.1, but of course, notable difference, the population standard deviation sigma is unknown, and therefore we introduced and utilized the notion of a t-distribution, which is eerily similar to a normal distribution, but with some very subtle differences. So with this information, we should have enough knowledge to tackle some of the homework problems. So work on those, and next lesson in section 6.2, we're going to revisit the notion of confidence intervals, but as they relate to a slightly different statistical concept. Until then, however, thanks for tuning in, and I'll catch you all in the next one.